Okay, gravitation.
So fine.
Now,
So
gravitation's first formula, F, right, the force is minus G m over r squared. Okay, field strength
and 0
is equal to minus G
okay.
m
So how to define any
over
identity?
r.
It is something or something give you back something. Okay,
Or minus G m over r squared.
That means this
The
operator.
third one is called potential.
Operator. Okay.
Gravitational potential is minus G
This is what identity.
m m.
You get very more complicated if things are not.
Third one is potential G plus
or function by individual. Okay, for example.
over r. The fourth one is potential
Yeah,
is minus
so
G
sine
m
what
over
equal
r.
to
Right, four things, right? Now the first thing is that what's the meaning of minus? Okay, minus indicate
this very cheap things here. So it's like later you know, okay.
inward. Okay, what's the meaning inward? Not really. If I have an object, okay, which will radiate a field, that means I will have an area, affect an area that will
Don't play with it, you can play inverse.
radiate a field. Okay, that means there will be an area that will affected by me. Okay.
So
Normally, I would say
what
that
is,
it's going to have
we know what's operator now.
something that affecting one another from my body. Okay. So
So
normally, right, people would define outward from the object to be positive.
But this is about how you find identity.
Because they say, let's treat it as positive, we say positive. Okay. So then they
discover
discover the gravitational force, right? If you have an object here, the force is going to be
and this symbol
by this,
-1 there.
the force by this guy
-1
will be the force on this guy and towards this guy myself.
Something put
So therefore, it says this force is negative.
That means it's
Okay?
the power
Negative
-1.
means towards
Sometimes
the
something
object.
put the
Okay?
minus
So
one
they say,
is
people say that
So the
minus
operation.
indicate, in here indicates
very limited.
directions, which is towards the body. Okay? But this one, right, the minus signs,
This
right,
is not equal to
do not indicate direction because they're scalar.
Okay.
Okay, so the idea is that it indicates below zero. So the value is less than
Sometimes
zero.
they're going to put it in
Okay.
outside. Okay.
So why is that less than zero for this case is that when you have an object, okay, and in this object, right, there's no reference point. So, okay, so they need a reference point. And secondly, they set this reference point a number. So in our number system, we have positive infinity to negative infinity. So which is the good number to set? A very unique number that everything refer from there is. So what's a nice number is zero.
With inverse A, right?
You got positive infinity, negative infinity, right? So zero is actually one of the very good reference points outside for these things. So we start with zero. Second thing is that where can I have a position? Where can I have a position that for all objects in this positions right here
and then write out the
will have
something
the same effect for all kind of objects in all variation you can have.
If you have
The idea is you can't,
the operation is
except this point is out of my influence.
so
When it's out of everybody's influence, this point is M. The status of this point is F is the same for everybody. So this is the only reference point is possible, and that's the only reference value is possible. Therefore, we define at infinity the whatever potential is zero.
3 plus
Position
0 equal to 3, right?
This is the value.
So the additional identity is
And they got no
0.
choice.
Because you add 0.
Because you talk about the line surface, it depends on the size. And even though the same size, it depends on the mass.
What's this?
So it's very hard to get a standard. So there's only one standard, which is infinity, and there's only one standard where it's called zero. So this is why they said infinity
So
is
minus 3, right?
zero. Because they said infinity is zero,
Verse.
that's the problem is that when the object comes into this field, right, if you need to push against a force, let's spring like that, you need to push in against a force, you get bounce back. So at this instant, those energy that you push in, right, is stored inside this object here. So it become a potential energy. And if you keep pushing inside here, right, the amount of potential energy will be positive.
You time what?
Make sense?
Is no effect one.
Okay, because I really store some energy
One
inside.
is the identity.
But on the other hand, right, if you
So you time one, you get back 1.
on the other hand, if you
3 times 1, so you get 1.
but too bad if that this force right in here right is actually attraction force. So therefore, instead of you need to push in energy, right? No, it actually gives you energy come back. And if you want to bounce back kind of things, right? So actually you need to supply. So this one says the amount of energy stored here is going to be less than 0. It's not a positive potential energy. So on the other hand, the thing about it is actually negative potential energy. So this one, this minus sign does not indicate directions, tells you that the value stored in the object,
inverse of 3.
it is negative.
And minus 3 is the additional inverse of 3. Okay. Do you understand?
Yes.
Do you need to remember?
No.
Okay?
Yes.
So
okay.
remember. So this is why when you draw it out, that means at the instant you draw out your arrow,
inverse
indicates the direction. So you no longer need to put a minus sign. But in the universal definition, the time there is a minus sign here indicates that the force is inward, or to say it is an attraction force. Okay? And interestingly, right, attraction force always will give you a negative potential energy because of the differentiation integration things. Okay? So
A inverse of A will give you the identity of B.
Force distance graph. Okay? We can't think like that.
Have identity.
If you integrate the area,
as well as B.
integration of your force different and the distance x, right?
Cancel the
It should give you the energy of your movement. If it is from here to here, it's from here to here, there will be no energy gains or energy loss and other things. Okay? So this is the integration relationship. Therefore, on the other hand, right, if you have a energy distance graph, right, the gradient
because if they
will be the differentiation of this with this. So therefore, the gradient is force. Okay?
2x plus 7 over 3 equals
so this is how the force and the energy are related. Okay? We say that.
Why is it 100?
Because
wait, yeah, you're right. But 3
we say that
of this
force
divided by
is
3
the
times 3
minus differentiation of your distance.
So
and this one tells you the directions, okay, which is from the positive x. Positive x is defined as from the object go outward. Okay?
and then
So this is x. Okay, so it's from the object to this point. Okay, so this is y force equal to force equal to minus du dx.
When it gets complicated, the reason
So
is
secondly is that why is there field strength? We say that force is not good enough because if you have a planet A, you have a planet B. Okay, if you apply an object, right, which has the same distance,
we no longer write multiply. Please. No.
okay, when this thing
You say
is experiencing 100 Newton,
number,
and this thing is experiencing 100 Newton, okay, same distance, same 100 Newton, does it mean that the force is same? May not be, because these things, right, can actually be 200 kg, whereas this is only 2 kg.
The most you do is the dot.
Okay? So the idea here is that just by judging the force and the distance, right, cannot tell you which one will have a stronger gravitational field.
Mix up with your
But this why force cannot be a kind of thing called the strength of your field.
So
unless you say I'm going to have this divided by the kg, so it is it becomes 50 Newton for every 1 kg. This then you have realized that this is 100 divided by 200 equal to actually 0.5 Newton for every kg.
We have 2 divided by 4.
Therefore, you can see that the strength, the field strength of this guy is stronger than this guy because every 1 kg you have 50.
Tell me,
Every 1 kg you have 0.5.
divided by 4.
So this place, right, since it's this place, right, whatever the object it is, you divide it by its mass.
over 1/4, right?
So actually, you no longer have the object in your picture.
Yeah, very right.
It actually tells you at a position, a point,
Time it so that you flip
and
right.
how many Newton for every 1 kg
Yeah,
is
you can do
there.
that also.
So it's by this guy, with respect to a point here, a
space
space here, okay, without considering any objects.
Whichever way, okay.
So any,
Because
how many Newton will experience in 1 kg. Okay? So the idea is that,
hit this as
once you understand this, right,
now this is something like A over B.
once you understand this, you know that
Or you can have A over D
field
over
strength,
C
right,
B inside over E over
it's
M.
actually
You have
force
log.
per unit
The
mass.
idea is which is longer, which is smaller. Okay.
Okay?
A very
So
easy way.
field strength actually is kind of like a force, but it depends divided by the mass of the one that being affected by the force. So it's the same issue. Why they talk about potential? Potential is actually potential energy per unit mass. Okay? So therefore, it is actually an amount. And so if you have an object, okay, the idea is that at this position, if you put 1 kg, how many joule of potential energy you should have? So let's say 50 joule per kg. That's what we call the potential.
Okay.
That means when you put 1 kg here, you have 50 joule potential energy. Okay, of course, it should be minus 50 joule, it's all minus here. Okay, so therefore, you see the four with of them all related this way. Force, field strength, okay, and then you have energy, potential. Okay.
numerator. denominator 去到呢就條 numerator。
2 times 3.
Okay. This relationship is always divided by the mass. Kind of things like divide mass means the standardization of only the field provider. It's a standardized force at a position with respect to the field provider only. Okay, this is including the affected object. This to this, right, is the differentiation. Oh, sorry. It's more beneficial to think this way. Differentiate the u minus du dx is the force. So minus d of potential dx, right, is field strength. Okay? Okay. Why is it minus? Okay. Because because the u graph is in this way. Okay. So if you use the final minus initials, right, you will be lesser number subtracted by a bigger number, so you get negative. Okay. So negative means that the force is in this one. Okay. So therefore it is negative. Okay.
咁你有啲譬如話 2, 3 minus
rub away. Erase this. I didn't say this. Didn't say this again.
4 minus 3 咁樣。
The graph of the u, okay, is supposed to be this way.
The minus only. Okay.
So when you do the gradient, right, you actually have positive gradient. Okay? Because you take next one, this one, you can have positive gradient. So positive gradient, right, so this one you need to put a minus sign because you know the force is towards the object. And the force for the negative, but the gradient is always positive. Because the graph is this way. So this one is minus du dx
actually
minus d.
Another way of writing is this.
Whatever dx, okay?
And we have this.
Okay, so after that, we talk about this. Okay, we talk about some very general things. Resultant x is always add up all the x.
So when you see the left up corner have a number,
okay,
it just means
one. But after that, you ask yourself, is it vector or scalar?
Just like that.
If it's scalar, numerically add up.
Right, more and more.
If it's vector,
they give you things like wow.
Add them in the vector with draw them out. We solve the components.
Okay.
Okay. So
how
just
can it look
add them out
correctly.
correctly. If it's scalar, so what the idea is that two individual, you calculate individual value. After the tell yourself, these individual values are all scalar, scalar.
So we can
then you just add it up. Will be the resultant at the bottom. If it's a vector, you add in the vector way, and then the resultant will be the answer. Okay. Now, different in anything is always anything final minus anything initial.
Put it as
okay.
7,
But after that, you also got to ask yourself, is it vector or scalar?
Okay. And then inside.
If it's a scalar, numerically subtract it, the answer is a number. There's no direction.
Okay, but come on, you.
If it's a vector, draw out the initial vector, final vector, and then say final minus initial. So this is the answer. Okay. So the answer is a vector, vector 1. It may not have meaning, but who cares? Okay. So vector is vector, scalar, scalar, do accordingly. So you know when you have some system like 1, 2, 3, 4 things affecting something like here, and some I don't know what how many meter. That if they say, oh, what's the resultant potential energy? Then with this do this object, this object, you have 4 values. 1, 2, 3, 4 here. Okay. And after that, tell yourself, right, it's a scalar, so you just numerically write them up. Only 2 cancellations. But it's a force, then you draw. Okay. 4 of them calculate separately, and then after that we solve them in a vector way. Okay. So it's just some common vector calculations. Okay. So what's next? The next thing is geostationary. Geostationary object, and then Kepler's third law, something like that. Okay, object need to be geostationary, which is interesting. Okay, this is the Earth. Okay, let's say rotation is in, okay, like that. Okay, so if you want your object to be in geostationary, right, most probably is that you want to say is that when my object is on the spot of the Earth, when this spot keep moving according to the Earth rotation, this object will still on the same spot. That's what we call geostationary. Okay. Now how does it achieve? Okay, it can be achieved if your spot rotate 1 mile of the Earth, the same as your object will rotate 1 mile of Earth, and it's at the same spot. So the idea is that they need the have you learned centripetal force? Yeah. So you need the centripetal force equal to the gravitational force. Okay. Now I don't have to put a minus sign there because it indicates direction. Okay. So these two values got to be the same. Okay. So therefore you see R cubed omega square equal to Gm. Okay, and you can calculate you can make the omega inside have 2 pi over T. Okay, this is the mass of Earth. Okay, 2 pi over T. This is a period. Okay, so you just need to set the period to be 24 hours to second. Okay. Therefore, you calculate this, you know the radius. That means the object will be how tall it is. Okay. So you know that for a fixed period that's rotating about Earth, if its rotation is purely dependent on the gravitations, okay, then the period square is related to the radius r. Okay, if you open this up, go over, you see r cubed is proportional to t square. That's Kepler's third law. Okay, so whatever period you want it to rotate due to the things, it just shoot it up to the whatever radius. Okay, the distance from the Earth core. Okay, so that's the Kepler's third law. But anyway, this object, right? If you want to be this way, you need the centripetal force to be equal to gravitational force. Okay, so the problem is the centripetal force is the force that is pointing towards the center of the rotations. So if your object is not on the equator, okay, the force is in this way to the Earth center. But the Earth, right, is rotating according to, so it is on a spot which is not at the equator. So what happens is that if you say this is the gravitational force equal to the centripetal force, right? The rotation of this object will be in this way, which is not along the directions of rotation. So this is why, right, the country is rotated in this way, but my object is rotated in this way. So therefore, it cannot be in geostationary. Okay. So the only possible geostationary object is that when the object is on the equator, the country is rotated in this way, your force is in this way, so you will also rotate this way. Okay, so that's the reason why your object must be in the equator. Okay, after that is something called escape velocity, right? Yeah, I still remember those things. Escape velocity means that I have something that can escape the gravitation. Okay, so let's say this is infinity. Okay, this is the positions where you have. The idea is that the initial kinetic energy I need to have in my rocket or propeller or whatsoever, okay, must be enough, okay, to overcome the change in potential energy. Okay, so the change in potential, so this is why Ke must be greater than or equal to Pe final minus Pe initial. Okay, and Pe final is the infinity. It's infinity, right? Infinity is treated as 0. Okay, and the initial is minus Gm n over r, right, which is at the surface here. Okay, so therefore half mv square, and see minus cancel, so therefore you have v square greater than or equal to 2g m over r, and then v is greater than or equal to square root of 2g m over r. Okay, that means the initial speed must be at least this amount, but I think this is not so good to remember, okay? Because all you need to know is that how much energy is needed. You can always come up with something. For example, let's say the rocket is already in certain height from the Earth. I want to escape. So from there onward, how much? Then you just do accordingly. And how much of a kinetic energy must be at least there to go against all these things. Okay, so that's the escape velocity thingy. Okay, who cares about it? Then the next one. What else? Gravitation. Okay, first law. Next one is that things happen inside Earth. I don't know whether you learn it. Yep, things happen inside Earth. When it is this is something called the effective sphere theory. Okay, so if you have a planet Earth, okay, if you have an object, if you're on at here, okay, and if you have a here, if you have a here, okay, the gravitational force that you experience by this guy or this object, right, will be an effective sphere things here, any mass that's inside. Okay, take your specific point you consider as the tangent. Okay, draw a circle. Then you see in this one you are affected by this mass. So that's why you have the force equal to gm m over r square. Okay. In here you draw effective sphere. You still have the same mass here. So this is why gm m over r square. When you're here, you still have the same whole sphere, so it's gm m over r square. But once you are inside here, you're inside here, then your effective mass is only this amount. Okay? So therefore, you see, right, the mass is no longer the big mass. So how to do all this? The force? Okay? All you need to do is express the mass in terms of the density and perfect sphere. Okay? So equal to g m changed to mass, density equal to mass over volume. So mass equal to density times volume. Okay, the volume of a sphere is 4/3 pi r cubed. Density is rho. Okay, and then m over r squared. And then you can see, right, this r and this r means the same thing. Okay, this r is the r from the center of mass to the point concerned. This r is the r of this effective mass. Okay, so therefore these two get cancelled. You get g 4/3 pi rho m. You only have r. So this is why they say okay. Let's don't talk about the negative sign for the vector. Outside the Earth, okay, you experience g m m over r squared. Okay, the force. But inside the Earth, right, you will have g 4/3 pi rho m r. So it's proportional to r. Okay, so this is proportional to r. This is proportional to 1 over r squared. Okay, so that's what happened if it's inside Earth. Okay. So what else in the gravitation? Yeah, one more gravitation thing is about the some common phenomenon. You can see that when in the science center there, right, there is a round table. Inside have a hole here, and that kind of things. Something like that. Then they have a metallic ball or beam. Okay, they just go around, and slowly go inside and then drop inside, right? Something like that. Now, what happened to these things is actually a good simulation about the loss in energy in a perfect orbiting system, lost energy. What happened? Okay, that's what I say. So if you have an object, it's supposed to go around the planet. Okay, if there's no energy loss, it will forever be there. Okay, so you already have certain KE. Okay, and then you have certain PE, GPE, okay? And you know that they are related. Why? Because in order for you to have in order for you to keep orbiting here, the centripetal force, right, got to equal to your gravitational force. Okay, so you cancel a little bit here, okay, for fixed r radius. Okay, this is fixed. If the r is fixed, right, the v is fixed. So you need to have this v so that you keep orbiting in this area. Okay, so what if your v is greater than this v? You will shoot out of the locus. Okay, what if the v is less than this v? You start to drop in. Okay, see whether you can keep dropping to Earth. Okay, so a specific height, a specific v, according to this formula. Okay, so what happens is that when you lost energy, right? Okay, of course the total energy equal to Ke and Pe. Okay, total energy must drop. Okay, then you will drop some this and you come to this orbit. But from this experience, you know that once it drops to a small orbit, it actually go faster. Okay, Ke actually increase, and actually P increase a lot more. Okay, so the idea is that when it comes down to the second orbit, you know that PE is smaller because the R is smaller. Okay, and the Ke you get increased because you do this formula again, you find the half mv squared is greater than the last one. Okay, or just look at this way, so you see mv squared over r. So I throw the r over, you left this. Okay, and the half mv squared, right, is equal to half of gmm over r. So when r drop, right, your half mv squared increase. Okay, so therefore actually once you go to lower orbit, the speed will increase. Okay, but the p will increase further because total energy got to decrease. Okay, because why? The loss in energy, the PE is gm over r. So if you load this, but it's minus sign, right? Okay, so from this one you drop a bit, the denominator gets smaller, but it's negative sign. So just now it's more negative, now it's got less. Sorry, just now was less negative, now you get more negative. Yeah, more negative. Okay, so this one, that one dropped a lot more than this half of this factor. Okay, so the total energy is lost. That kind of thing. So you can calculate it. Okay, so that's the way to relate the kinetic energy to the half mv squared. Also think about the centripetal force. Okay. Anything else you want to ask in the gravitation? This is roughly all of them. Good. Any other thing you want to ask?
No.
Okay, good.